Hello students, welcome back to my YouTube channel. So basically what we discussed in the previous video, that the basic concept of some coordinate chemistry and some ligand, about some ligand we will discuss. So today we will discuss about the topic isomerism. आज हम लोग आइसोमरिज्म के बारे में थोड़ा डिस्कस करेंगे. तो कोऑर्डिनेट केमिस्ट्री का एक बेस्ड टॉपिक है आइसोमरिज्म. व्हाट आर आइसोमर्स? Isomers are the basically the compound which have the same chemical composition but different posture, like different posture. So basically if we divide the isomers into two types, then we can tell that there are two types of isomer in coordinate chemistry. One is structural isomer and another one is stereoisomer. So coordinate chemistry or in coordinate isomer, we can divide the isomer into two types. One is structural isomer and another one is stereoisomer. What are the structural isomer? The structural isomer are divided into some categories which are known as ionization isomer, like hydrated isomer, like coordinate isomer, linkage isomer, polymerization isomer, etc. Okay, so we discuss the type of isomer one by one and take some example of every isomer. So first discuss about structural isomer, and under structural isomer we discuss about the ionization isomer. Before discussing the ionization isomer, we have to tell that there are some two types of sphere in present in complex compound. So one is known as coordination sphere. One is known as coordination sphere and another one is known as coordination sphere, and another one is known as ionization sphere. What is coordination sphere? The compound whatever written in between the third bracket, that is known as the coordination sphere. Okay, so basically with the metal, the ligand which attached with the metal is known as coordination sphere, and the ionic species or molecule outside the third bracket is known as ionization sphere. So if we consider an example like cobalt with 5 ammonia and bromine, and outside if we written SO4, that is the ionic species what is known as ionization sphere, and the metal with its ligand attached with its ligand, and if we tell that whatever attached with the ligand, that is known as the coordination number also, that is depends on its coordination number also, and this is known as the coordination sphere. Okay, so metal with its ligand known as coordination sphere, and the ionic species or molecule is known as the ionization sphere. So what is ionization isomer? What is ionization isomer? How we recognize an ionization isomer? Now in case of ionization isomer, the exchange of ligand in between coordination sphere and ionization sphere. Okay, so in case of ionization isomer, the exchange of ligand between coordination sphere and ionization sphere occur. Okay, so if we take some example, we can see that. Let us take this example. If we write CONH3 whole 5 bromine, and outside of its third bracket SO4, where SO4 is the ionic species. This is one type of complex example of complex where 5 ammonia and 1 bromine is attached with the metal cobalt and known as the ligand. 5 ammonia and bromine are the ligand, and where SO4 is a ionic species or ionic molecule. Okay, so if we rewrite or if we exchange the ionic species inside the third bracket and outside the third bracket, okay, means if we exchange the ionic species of coordination sphere and ionization sphere, then we can rewrite the complex as cobalt NH3 whole 5 SO4 and 1 bromine. So we can tell, now we can tell that these two are ionization isomer. So how we recognize an ionization isomer? In case of ionization isomer, the ionic species between the coordination sphere and outside the coordination, sorry, inside the coordination sphere and outside the coordination sphere can be exchanged, and whatever we get, that is known as the ionization isomer. Whatever we get, that is known as the ionization isomer. Okay, so if we take one more example, we can see that if we write cobalt 5 ammonia and 1 nitrate, and outside of the coordination sphere we write same ionic species SO4 sulfate, and in another case CO NH3 whole 5, this sulfate enter inside the coordination sphere, and this ammonia, we write this ammonia outside the coordination sphere. So that can be a possible isomer. That can be a possible isomer of this complex. Okay, so these are the example, some example of ionization isomer, and we can say that in case of structural isomer, the two isomer are invertible, interconvertible. Okay, so the two isomer can be interconvertible but without breaking the metal ligand bond. Okay, so these two isomer can interconvertible without breaking the metal ligand bond. Okay, so the next type of isomer we write hydrated isomer. So what is hydrated isomer? You can easily guess that the hydrated means some H2O molecule is, obviously some H2O molecule is there. Okay, so when water molecule exchange between coordination sphere and ionization sphere, when water molecule exchange between coordination sphere and ionization sphere, that is known as the hydrated isomer. So if we take the example now, Cr chromium H2O whole 6, and outside of the complex 3Cl is present, then we can write chromium now H2O whole 5 1 Cl. If we take one chlorine inside and one water molecule outside, and rest of chlorine also outside of the third bracket, then we can say that these complex can be the hydrated isomer. So if we take one more cases, if 4 water molecule is inside the coordination sphere and 2 chlorine molecule, and outside of the sphere 1 chlorine molecule and 2 water molecule, then what we called, now these three are isomer to one another. Okay, so what are the difference? They are differentiate via some physical property and also chemical properties. So if we talk about the physical properties, we can easily see the change of color. So in case of first example of this complex, we can see that these are the violet color. This complex shows violet color. Okay, and this complex shows pale green color, and this complex shows dark green color. So we can easily we can easily see the with our naked eyes the change of the color of the three isomer of the complex. Okay, so these are known as hydrated isomer of the complex. So we can easily recognize an hydrated isomer of the complex. What is an H2O molecule, an hydrate molecule, and water molecule is obviously present in between the complex. So such type of example are coming in several exam uh, several exam that in out of the four following example, what is hydrated isomer, which complex is hydrated isomer. So we can easily recognize via H2O molecule. So obviously an H2O molecule is present in case of hydrated isomer. So if we take the next concept about linkage isomer. So what is linkage isomer? So what is linkage isomer? In case of linkage isomer, an term ambidentate ligand we already discussed in my previous lecture, in my previous video. So what is ambidentate ligand? Ambidentate, there are the basic difference we told already. There are the basic difference between ambidentate and chelating ligand. What are the ambidentate ligand? Ambidentate ligand have the more than one donor center. Okay. In case of ambidentate ligand, there are more than one donor center, and also in case of chelating ligand, there are more than one donor center. But in case of ambidentate ligand, the all donor center are not active at a time. Hmm. Only one donor center is active at a time in case of ambidentate ligand. Amphibian, what is means of amphibian? Amphibian means जो species वाटर और वाटर में भी रह सकता है और मीन्स लैंड पे भी रह सकता है. ठीक है, उसको हम क्या बोलते हैं? उसको हम एम्फीबियन बोलते हैं. बट एट ए सेम टाइम, एक ही टाइम पे वो एक ही जगह में रह सकता है, या तो वाटर में या तो लैंड में. ओके. सो इन केस ऑफ लिंक, इन केस ऑफ ambidentate ligand, what we mean from amphibian, that in case of ambidentate ligand, there are more than one donor center, but at a time, only one donor center is active. Only one donor center donate its electron towards metal. But in case of chelating ligand, the all donor center are active at a time, like ethylene diamine. We already discussed about the example of ethylene diamine and ambidentate ligand and chelating ligand. So chelating ligand example is ethylene diamine, where two nitrogen donor center is there and two donor center are active at a time. Two donor center donate electron at a time towards metal. But in case of linkage isomer, we all only discuss about the ambidentate ligand. So linkage isomer arise when an ambidentate ligand can coordinate with the metal cation. Okay. So an ambidentate ligand is coordinate with the metal cation. So if we take an example of ambidentate ligand like NCS, where there are two donor center. What are they? One nitrogen and one sulfur. So if the ambidentate ligand coordinate to a metal cation through either of the two different atom. Okay. So if we consider the metal as cobalt and write the isomer like NH3 whole 5, cobalt NH3 whole 5 NCS, and outside of the coordinate sphere we write Cl2. Then if we tell that nitrogen is active in this complex, so we can write the another example where sulfur is active. So these are the the possible linkage isomer. So linkage isomer always tells about the ambidentate ligand which have more than one donor center, and on the basis of the donor center which is active at a same time, which is active at a particular time. So on the basis of the donating center, we can differentiate the number of isomer. We can calculate the number of isomer. Okay. So if we take one more example, CO ENR whole 2 NO2 whole 2. Okay. So what we told about EN is the chelating ligand. This is the chelating ligand, not the ambidentate ligand. Chelating, and this is ambidentate. Ambident. So if we tell that this nitrogen is active in this case, this nitrogen is active in this complex, then in another complex or another isomer, we can write that this oxygen is also active center. So ONO whole 2 we can write as the isomer. Okay. So these are the example of linkage isomerism. Now we can discuss about the coordinate isomerism. So what is the example of coordinate isomerism? In the competitive exam, they discuss the question are coming like out of the 4 following cases, which is the example of linkage isomerism, which is the example of hydrated, which is the example of ionization isomerism. So direct question coming in question. Okay. So if we once if people just recognize the types of isomerism and how the types of isomerism bind, so then you can easily find the example of the question. So in case of coordinate isomer, what happened now? Two types of complex are given in this coordinate isomerism. Two complex are given in this type of isomerism. So here the exchange between species or exchange between ionic species. What we discuss about the ionization isomer. In ionization isomer, we discuss about the ionic species. What is exchange between coordination sphere and ionization sphere. Okay, but in this case, coordinate isomer, the ionic species exchange between two complex. Between two complex. Like if we take an example, cobalt NH3 whole 6 and chromium CNR whole 6, chromium CN whole 6. So this is a type of example like two complex are bind, or two complex are we write two complex at a time. Okay. So what are the example of what is the isomer of this coordinate isomerism? So if we find the isomer, we have to exchange the ligand. We have to exchange the ligand. Like here we can see that ammonia is bind to cobalt and cyanide is bind to CN is bind to chromium. So when we write the coordinate isomerism, then we write cobalt is bind with CN6 and chromium is bind with NH3 whole 6. Okay, so we can see that in this type of isomerism, the exchange of ligand occur in between the complex ion. So in case of coordinate isomerism, you have to find this type of two complex example. Okay, so if you find the complex example, then you can easily decide what is the example of coordinate isomerism. So now the next topic is polymerization isomer. Polymerization isomer. So what is the polymerization isomer? Polymerization isomer. Uh, these are not the real isomer. Firstly, we have to tell these are not real isomer. All these isomer have the same empirical formula only. That means the ratio of metal and ligand are always same of every isomer. The metal is to ligand equals to always same. The ratio of metal and ligand are always same. And what is the ratio? The ratio should be 1:2:2:2. 1:2:2:2. So if we tell platinum NH3 whole 2 Cl2, so here what we write, Pt2 plus ammonia and chlorine. Okay, and if we write platinum NH3 whole 4 and platinum Cl4. So what we see? We see that the number of platinum is here 1, ammonia 2, chlorine 2, and here also, and ratio should be 1 is to 2 is to 2, and here also platinum 2, ammonia 4, chlorine 4. So here also is the ratio same. So what we told, that is the ratio between the metal and ligand will be same, always will be same. Okay, these are the example of polymerization isomer. The empirical formula should be same in case of every isomer. So now these are the common basic example of some isomerism, and also there are some isomer like ligand isomer, coordination position isomer. So that are the not important so much, but what we discuss like ionization, hydrated, linkage, coordination, and polymerization, the question are coming from these isomer, and that are the very important example. Directly question came in several type of competitive exam. Okay, so now we discuss about the stereoisomer. So in case of we told before that in case of structural isomerism, the two isomer can be interconvertible without breaking the metal and ligand bond. Okay, in case of structural isomerism, the two isomer like this isomer and this isomer, they are interconvertible. Okay, without breaking the metal ligand bond. But in case of stereoisomer, we cannot interconversion the isomer with without breaking the metal ligand bond. Means if we want to interconversion the two isomer, then we must have to break the metal ligand bond. Then only we can exchange between the isomer. Then only we can interconversion the between two isomer. Okay. So now if we talk about stereoisomer, stereoisomer. So stereoisomer are basically two types. One is geometrical isomer and another is optical isomer. Geometrical isomer, what is geometrical isomer? Now, based on its geometry or its stereochemistry, means obviously we think about the cis and trans. So in case of what we know, in case of where the double bond is present, in case if same type of species present at the same site, that is known as cis, and if the same type of species present at opposite side, that are known as trans structure. So in case of geometrical isomer, this concept help us. Okay, so optical isomer we discuss later. First we take some example of geometrical isomer. So in case of geometrical isomerism, if we talk about the so in this topic the how the question come. Now the question is coming that like what are the number of stereoisomer present in this complex, what are the number of geometrical isomerism present in this complex, what are the number of optical isomerism present in this complex, and that type also coming which in out of this following cases, which example is optically active. So this type of question coming in competitive exam. Okay, so if we want to know the idea of geometrical isomerism, we have to divide some cases. So like if we consider coordination number 4, means one metal is bind with 4 different type of ligand, then we can see that if we tell MA2BC, in these cases M is metal, considered as metal, and other alphabets are considered as ligand. So we can see that the metal is bind with 2A and 1B and 1C. So we can write like metal is bind with 4 ligand. So if we write 2A and B and C, so we can see that 2A are on the same side. So this is known as the cis isomer. And if we take one A and another A are opposite side, then we can tell this is the trans isomerism. Okay, so in this type of example, coordination number of 4 is not so vast, not so various type of example is there. But in case of coordination number 6, CN6, we can tell some isomerism, the number of isomer present in geometrical isomerism. So now coordination number 6. Now we talk about the coordination number 6. So in case of coordination number 6, there are a various type of example like M, A, B, C, D. M, A, B, C, D, E, F. If a metal is bind with 6 different ligand, then it is a type of isomer. If metal is bind with A2, B2, C2. So these are the type of example we can set. Like we can set the different type of ligand via different type of its based on the its donating capacity. So if we write the 6 different ligand, then this is a type of isomer. If we repeat the 3 ligands twice, then this is another type of example. So now first we discuss Ma2B2C2. In case of Ma2B2C2, there are 5 isomer possible. 5 isomers possible. In the last, at the last of the video, we discuss about a basic trick how to calculate the number of how many number of isomer present in a particular structure. So we discuss at the last of this video. First we discuss Ma2B2C2. So in case of Ma2B2C2, there are 5 isomer. So what are the 5 isomer? First we draw the skeletal. It's easy for me. So first 2A, 2B, 2C. Now 2A, 2B, 2C. Now 2A, 2B, 2C. 2A, 2B, 2C, and also 2A, 2B, 2C. So these are the 5 isomer we can set of this particular complex. Okay. So same case, M, A, B, C, D, E, F. If we set the 6 different ligand at the same time, then there are 15 isomers possible, but only 3 isomer isolated. इसका only 3 isomer isolate किया गया है, but 15 isomer possible हो सकता है. Okay. Okay. So now how we can calculate by only seeing the complex. Now by only seeing the types of ligand present in this complex. So that is the basic. They are just basic trick. Not such a trick like you have to only determine the structure by drawing it. So if I tell something, then there can be a trick, basic trick, what is maybe applicable some cases. So we can discuss it later. Okay. So now a very important isomer. What is Fesmar isomer? What is Fesmar isomer? Fesmar isomer means Fes means here facial isomer and Mar for meridional isomer. Meridional isomer. Okay. So in case of what is facial isomer? In case of facial isomer, first we if we talk about the skeletal of this complex, so only three isomer possible: Ma3, B3. Okay, this can occur only for octahedral complex. So in case of facial isomer, three identical donor atom lie on the triangular face. Okay, so in case of facial isomer, the three identical donor atom lie on the corner of a triangular face. So what letter? Okay, then what is meridional isomer? In case of meridional isomer, uh, three identical atom cut the isomer, or we can say the three identical donor atom lie on a plane. What is bisecting the complex? Lie on a plane. What is bisecting the complex? What is means? So तीन आइडेंटिकल डोनर एटम एक प्लेन में होता है जो प्लेन एक कॉम्प्लेक्स को बाइसेक्ट करता है. ओके, सो इन केस ऑफ फेसियल आइसोमर द थ्री आइडेंटिकल डोनर एटम lies in the corner of a triangular face. If we consider a triangular face in a complex, then the three identical donor atom lie the corner of three vertices of the triangular faces. Okay, and in case of meridional isomer, if we consider a plane what is cutting the complex and bisect it, then we can consider the three identical donor atom present on the present on the lie on the plane. So if we take the example, we can easily consider, like if we take cobalt NH3 whole 3 Cl3. Okay, so the metal is here, and if we consider 3 ammonia and 3 chlorine, so this is the facial isomer. So you can easily consider that this is the triangular face. This is the triangular face, and in this triangular face there are three vertices. Three vertices are occupy three ligands, same donor, three ligand or three same ligand. Okay, so if we draw the octahedral structure properly, actually it is a 3D structure. So in case of 2D, it is quite impossible to draw. Okay, this is in the plane. So if we consider a paper, if we consider like a like this, if this plane, then what you can understand, that metal is present in the center of this writing pad. Okay, if we consider the writing pad as the complex, then metal is present as at the center of the writing pad, and the four corner occupy four ligand. Okay, now one ligand is upside the upside the plane, and one ligand is attached in downside the plane. Okay, so like upside the plane one ligand is present, and downside the plane one ligand is present. So now if we consider the facial isomer, so what we can see that the above position or the axial position, one of the axial position occupy one ligand, and if we consider a triangular face like this this two corner and this axial position. Okay, so if we connect these three positions, so one triangular face we can see, and in this triangular face three same donor site are attached. Okay, so if we draw this structure via 2D, so one metal ligand is present upside the plane, and one another metal ligand bond is present downside the plane. Okay, so now if we talk about the same ligand, so we can see this can be a triangular face. This can be a triangular face. Okay, so this is a possible octahedral structure. So this is the triangular face. Okay, now if we consider the three different ligand, like if we consider ammonia, NH3 is here, another NH3 is here, and another NH3 is here, and the rest of three chlorine, one is here, and another is here. Okay, so we can see the vertices of this triangular face are occupied by three ammonia, which is a same or identical donor atom. Okay, so this is considered as the facial isomer. So easily if you draw the metal ligand bond, you can consider metal, and three ligand are consecutive, and another three ligand are L1, 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 and these three ligand L2, L2, L2 are consecutive. So this is the facial isomerism. And if we want to draw some meridional structure, then you have to L1, L1, and you have to write different ligand, what is different donor atom, L2, and again L1, L2, L2. Okay, so now we understand the 3D representation of the meridional atom. I told that the meridional isomer, in case of meridional isomer, the three identical donor atom lie on a plane. What is bisecting the complex? It's lie on a plane. What is bisecting the complex? Now, if we want to bisect a complex, we can see. So first we can draw the skeletal cobalt like metal, and what we write, ammonia. Oh, we can write L1, L2. That can easy for me to draw. L1, 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 and this one L2, different ligand L2 and L2. Okay, so now if we draw properly, then this should be on the upside, and this should be on the downside. Okay, we can increase the length so that we can cut it properly. Now if we want to connect it, we can see that these L1, these three L1 are these three same ligand forming a plane. These three same ligand forming a plane. Okay, what is the plane? Like this. These three same ligand forming a plane. What is cutting the complex into two halves? What are the two halves? One half is downside, forming downside, and another half forming upside. Okay, and this is the plane. What is cutting the complex into two halves? Okay, so this can be known as the meridional complex. Okay, so I can you people understand it properly. What is the basic difference between facial and meridional isomer? In case of facial isomer, there are three identical donor atom which lies in the corner of triangular face. And what is meridional isomer? In case of meridional isomer, the three identical donor atom lie on a plane what is bisecting the complex. Okay, so I think you people understand. Now, if we take the next example, like in this example, we can see the atom which donate two electrons at a time, or AA. What is the example of an chelating ligand? Okay, so in these cases, three isomers possible. Three isomers possible. What are the isomers? Example of isomers, and how we can consider this structure first. Take an example. So if we tell a metal is bind with 2 En, okay, or 1 En. This is En. Sorry, this is ethylene diamine. So if we talk metal ethylene diamine and B2 as a NH3 2 and Cl 2. This is the example of the complex. So this can donate. So in case of octahedral structure, 6 ligand are attached. So here 2 ligand, here 2 ligand, 4, and this ethylene diamine donate 2 electrons and fulfill the metal vacancy of 2 ligand by 2 ligand, like 2 ligand. Okay. So in case of ethylene diamine, it can consider as behave as the 2 ligand, 2 ligands. So total 6 ligands we can see. So in this case, how many isomer possible? Not 6 isomers possible. 3 isomers possible. So like if we consider the 3 isomers, one is that, and another one is two ammonia are sidewise, 2 Cl are also sidewise, and in another example, 2 chlorine are downside and 2 ammonia are sidewise. Okay, so we can told we told that this is the cis structure, like 2 ammonia, one is in the plane and another is axial. So this is the cis isomer, and this is the trans isomer where 2 Cl are so trans is dominating on the cis structure. Okay, so here we can see that if we talk about chlorine atom, then two chlorine atoms are locating one upside and another downside to opposite center. So this is the trans. So if you consider ammonia, so two ammonia are on the same plane. So that is not considered. Only two chlorine atom are considered. Like trans is always dominating. Okay. So here this is also a trans structure. We do not consider the chlorine atom what is on the plane. On the plane, we consider the ammonia atom. What is one is upside and another one is downside. So these two are trans isomer and one is cis isomer. And if we talk about the optical isomerism, so cis isomer are always optically active. We discuss it. Cis isomer always optically active. Okay, so now we discuss about the optical isomerism, and then some we tell about some topic, about some trick what we told before. Okay, so optical, in case of optical isomerism, which isomer shows optical isomer, or which is optically active? In case of stereochemistry, we know that if a light passes through a compound, then if the compound shows some rotation, like what is dextrorotatory, we called in stereochemistry, if we recall stereochemical chapter, then we read all previously that one is levorotatory and what is dextrorotatory. Two type of rotation can be possible. So dextrorotatory means it rotate positive side or clockwise, and levorotatory means it rotates negative side or anti-clockwise. So positive isomer are always known as dextrorotatory D, and this is L. So DL isomer we already read in stereochemistry. Now, what is optically active? The essential condition. What is the essential condition for a substance to be optically active? To be optically active, the compound must be chiral. Must be chiral, and there is no plane of symmetry. There is no plane of symmetry. Okay. So, to be optically active, the compound must be chiral, and there is no plane of symmetry. Like we, all, if you people read the group theory, then you can tell like sigma H, sigma V, what is the plane of symmetry, example of plane of symmetry. Okay, plane of symmetry means the plane which cut the compound into two halves. Okay, so this is the plane of symmetry, and according to the vertical and horizontal position, we name it sigma V, sigma B. Sigma is just a sign that there is a plane in this compound. There we can draw the plane in the compound, and totally this is imaginary. Okay, so there is a chance to cut the compound into two halves via the plane. Then, according to position of the plane, we can tell it sigma V and sigma H. Okay, so to be optically active, there should be no plane of symmetry. Okay, or uh, one more condition is there. If we draw the mirror image of the optically active, if we draw the mirror image of the optically active, then it must not be superimposable. Like if we draw the structure of a football, if you place a football in front of a mirror, then there is a same image we can see. Okay, so if you place a football in front of a mirror, then you can see the same image what is formed inside the mirror. Okay, now if you consider that you take this mirror image and place it above the object, then two image, or one object and another image. Okay, so if you placed an object in front of a mirror, if you placed a football in front of a mirror, then you can see the image of the football, and if you uh, take the football image to the main object, then there is no difference. They are superimposable. Like there is a term superimposable, means the image and the object are totally same. Okay, so these are the conditions to be superimposable. And what are the non-superimposable? Superimposable, impossible. Okay, so what are the non-superimposable? Now, if you see me, like these are the if you take your two hands, and one hand it's your mirror image of another hand. Now, if you take the image and the object, image on the object, above the object, if you take the image and place it above the object, then that there are no matching of the object and between in between object and image. So these are the example of non-superimposable. So if you take an easy example, then if you place this optically active word in front of mirror, then you can see some this type of mirror image. Okay, this is like that. Okay, like that. Only we can consider only active. Okay, so if you consider active word, then you can some mirror image like that. Like that. Okay, now if we place this active word above this active, ओके दिस उल्टा वाला एक्टिव को अगर हम सीधा वाला एक्टिव के ऊपर प्लेस करते हैं तो वी कैन मेक सब डिफरेंशिएट. बट इसी फुटबॉल को अगर इस फुटबॉल के ऊपर प्लेस करते हैं तो वी कैन नॉट मेक एनी डिफरेंशिएट. ओके, so if the differentiate between object and image after superimposable is after coincide is possible, then it is known as superimposable, and if it is not possible, then it is known as non-superimposable. So to be optically active, the compound should definitely non-superimposable mirror image. Non-superimposable mirror image. Okay, so in case of cis compound, there are always non-superimposable mirror image. But in case of in case of trans compound, there may be a chance to get a superimposable mirror image. And so what you learn, cis isomer and one more facial isomer, they are always optically active. Okay, they are always optically active. Now there is a and also in case of optical isomer, if we get one optical isomer of any complex, if we get one optical isomer of any complex, then the isomer should differentiate into two types. One is dextrorotatory and another is levorotatory. So in case of one, if the question comes, how many number of stereoisomer present in this complex, then if the complex has optical active isomer, then you should differentiate into two types, and when you count the number of stereoisomer, then you should consider the two types of isomer. So if you get one optical isomer, so this is that means there are two types of optical isomer, dextrorotatory and levorotatory, D and L isomer. Okay, so now trick to find the geometrical isomer. What is the trick to find geometrical isomer? So like if you consider the A6, a metal with 6 ligand. Okay, so first you have to write the possible combination like AA, AA, AA like this, and you have to interchange this ligand. If you have to interchange this ligand. Okay, so you get some get an idea about the number of isomer, possible isomer. So there is no exchange in all ligands are same now here. Here all ligands are same. MA6. So there are no possible geometrical isomer. So now if we consider like M A4 B2, then what are the possible arrangement? So AA 4A is there. So AA BB, and if we exchange the ligand, what should be a change? AA is fixed and AB, this is the another isomer. And what we write by via exchanging, then that would be same with these two isomer. Okay, so there are two possible isomer, two geometrical isomer, but there are no optical isomer. How I know there is no optical isomer? Because to present an optical isomer, if any two pairs, if any two pairs same, if any two pairs are same or same, okay, like if AA, two pairs are same, if AB and AB, two pairs are same, then they are optically inactive. They are optically inactive. Okay, they are optically inactive, not active. So if same type of isomer present, they are optically inactive, not active. So in this case, we can see that they are present also AA, AB, AB. So they both are optically inactive. Now, if we consider a different example, like MA3BCD, and you have a question, how many stereoisomer can be possible of this isomer? So first we rearrange the possible arrangement. A3 means you can just consecutive write the all ligands. Okay, so AA, 2A, AB, CD. Okay, now we have to exchange the possible arrangement, exchange the ligand and make the possible arrangement. So AA, AC, BD, AA, consider AD, sorry, PC. Okay, so AD, BC and AC, BD. Okay, one more is there. If you consider AB as constant, okay, so take AB as a constant and exchange between two, AC, AD, AC, AD. Okay, so there are four possible geometrical isomer. There are four possible geometrical isomer. Now we have to find the optical active and inactive isomer. So what we say, we told that if the same type of rearrangement are there, then that is optically inactive. Obviously, optically inactive. So if we find the that AB, AC, AD, there are no such type of same rearranged repeated rearrangement or same or like isomer. So this is optically active, and the rest of all isomer like AA is there. Okay, AA is there. So so 3AA is there. So they are not optically active. They are optically inactive. They are optically inactive. So these are the possible. So if the question is come, what are the possible number of stereoisomer? Total number of stereoisomer. Stereoisomer. So total number of stereoisomer means optically active isomer plus geometrical isomer or optically inactive isomer. Inactive isomer. So in case of optical active isomer, there can be two isomer more. One is D and another is L, dextrorotatory, lever rotatory. So what are the number of total stereoisomer? 1, 2, 3, 4, 5. Means in case of optically active, you have to consider two isomer. and optically inactive isomer 3. So total number of stereoisomer is 5. Okay, so that is the answer. The number of total stereoisomer is 5. Okay, so if you draw the structure, you have to follow this possible rearrangement and place the atom, like you can place it consecutively, but same rhythm. If you follow the consecutive rhythm, then you have to place it continuously like same rhythm: AA, AB, CD, AA, AC, BD. But if you want to place this ligand as diagonally, you can also place it diagonally, but you have to follow the same rhythm for all the 4 isomer. Okay, to draw the structure, you can't change the rhythm. Once you change the rhythm, the isomer should be the same like the another, like that another one isomer. Okay, so this is the whole isomerism, complex isomerism, and next day we discuss about the IUPAC nomenclature. In previous video I told that today we discuss about the um, IUPAC nomenclature of complex compound, but I think that IUPAC nomenclature should be learned after uh, learning isomerism. Okay, so I think that you all people uh, have got the idea what we talk about the isomerism, what we talk about the ligand, what are the some basic concept of complex chemistry. Now next day we discuss about the IUPAC nomenclature and some VBT, valence bond theory of complex compound. Okay, so I think you people all understand, and if you have got some problem, then comment on the comment section. Okay, bye bye, thank you.